Hi, in this problem we have a turntable which is rotating at a constant speed, and on top of that turntable we have a coin. Now as this disc rotates, it says in the question that the coin does not slip, so it stays on the disc rotating. So that's one clue you have as to how we can model the system. But before we look at that, let's take a look at the free body diagram of the system. So here we're looking at the turntable and the coin from a side view. So looking at it from the side. And since we're modeling the coin, we're going to draw a free body diagram of the coin. So first force that we're going to find on our coin is the weight. The weight acts downwards and it has a magnitude of m times g. Then we have the reaction force, or the contact force, between the coin and the turntable. I'm going to call that R. And then we have the friction force. Now, the friction force in this case is our centripetal force, and the centripetal force always acts towards the center of rotation. So Fr acts towards the center of rotation. The friction is the only thing keeping the coin on the disc. Therefore, it must be acting towards the center, as when you exceed the friction force, the disc will fly off towards the right. So that's our free body diagram. The acceleration is a centripetal acceleration, which acts towards the center of rotation. So it's going to be in this direction. Here we can call it A, C. Now to derive the equations of motion. We're going to have two equations, one in the x direction and one in the y direction. So let's start with the y direction. So we can say the sum of the forces in the y direction equals ma in the y direction. Now, since there's no acceleration in the y direction, we can see the only acceleration is in x. It doesn't matter which way we pick positive, let's pick up as positive. So the net force is going to be R, because R is going up, so that'll be positive. Mg is going down, so minus mg equals mass times acceleration, which in the y direction is equal to 0. So, rearrange the equation, we get R is equal to mg. That's one equation for our system. The second equation is in the x direction. So we can say the sum of all the forces in the x direction is equal to ma in the x direction. Now, since there's only one force and it's acting towards the left, same direction as our acceleration, we can say left is positive. So the equation is going to be Fr equals m times a. It's that simple. Now, since we're at limiting equilibrium, i.e. the coin is just about to slip, then Fr is equal to mu r. So mu r equals to m. Now instead of a, we're looking for the maximum speed that the turntable can rotate. Now, centripetal acceleration is also equal to omega squared r. Now, one more step we can do before we can start solving is that we've found here that r is equal to mg. Here we have mu r equals m omega squared r. So we can substitute the r from the y equation into our x equation. So the equation becomes mu mg is equal to m omega squared r. All we've done is simply substitute r equals mg into our equation down here. It's actually this r over here. So we can clearly see straight away that the two m's will cancel. Now we're trying to find omega, the maximum angular speed. So we can make omega the subject here. Start by dividing both sides by r, so it becomes mu g over r is equal to omega squared. Final step, square root both sides, so we get omega is equal to the square root of mu g all divided by r. Now let's substitute our numbers. We know that the coefficient of friction is 0.4 multiplied by 9.81 all divided by the radius, which is the distance between the coin and the center of rotation. And in this problem, that value is 0.6. Plug all these numbers in and you should find that your angular speed has a value of 6.54 radian per